July 13, 1943. Royal Aircraft Establishment, Farnborough, England. Wing Commander Derek Jackson stands in a lab surrounded by electronic equipment, studying the debris spread across 3 tables. The wreckage isn't from a crashed plane, but from a German Liechtenstein BC airborne intercept radar, which was recovered intact from a Junkers Ju-88 night fighter that landed by mistake at RAF Woodbridge 3 nights ago. The German crew had mistakenly thought they were heading to their home base in Holland. They were confused and disoriented, landing their plane upside down on a British runway. Before they could destroy anything, the crew was captured. The aircraft remained intact, including the radar system mounted in the nose, which had been responsible for targeting RAF bomber crews for 2 years. This radar allowed Luftwaffe night fighters to locate British bombers in complete darkness, turning night bombing raids from relatively safe to deadly. RAF Bomber Command had been losing planes since the summer of 1941. The loss rate during night raids over Germany grew from 3% to 7%, and then to 9%. By early 1943, some missions were losing 12% of their aircraft. The situation was grim. If you flew 30 missions, the chances of surviving were almost zero. These losses weren't random. They were concentrated. German night fighters using radar intercepted bombers, tracking them through clouds, following their evasive moves, and shooting them down before the bomber crews even realized they were under attack. British intelligence knew the Germans had airborne radar, but they didn't know how it worked, what it could do, or its limitations. Now, they had an intact system for analysis. Jackson's job was to dismantle it, understand every part, every circuit, every design detail, find weaknesses, and figure out how to save bomber crews who were dying nightly over Germany. Jackson was no typical military officer. He was a physicist. Before the war, he worked at Oxford studying spectroscopy. When the war started, he joined the RAF but continued to focus on applied physics, specifically radar, radio propagation, and electronic warfare. He understood the theory behind radar. Now, he needed to understand how this specific system worked. He started by photographing everything: the antenna array, the transmitter chassis, the receiver unit, the display scope, and every other component, taking multiple photos before disturbing anything. Then he carefully began disassembling the system. Each part was labeled and tagged, with its position recorded. The Liechtenstein BC was more complex than British airborne radars. It had more components, more amplification stages, and more sophisticated circuitry. The antenna array used 4 separate antennas arranged in a complex pattern. The transmitter generated pulses at 490 MHz. The receiver amplified returning echoes using high-gain vacuum tubes. The display showed both range and bearing. It was a remarkable piece of engineering, German electronics at their best. Jackson spent 4 days on the initial disassembly and documentation. By July 17th, the system was completely broken down, with components spread across the laboratory, schematics drawn, and signal paths traced. The detailed analysis began. He tested each component, measured performance, and explored capabilities and limitations. He started with the transmitter, connected it to test equipment, and powered it up. The transmitter functioned flawlessly, generating clean pulses at the specified frequency. The output power was around 1.5 kHz, enough to detect bombers several kilometers away. The pulse repetition rate was 3,750 pulses per second, standard for this type of radar. There were no issues. The transmitter was well designed and manufactured. Next, he moved to the receiver, which determined the radar's performance. The receiver needed to amplify weak returning signals, filter out noise, and provide enough gain to clearly display targets. Jackson examined the receiver chassis, which had 12 high-gain RF amplifier vacuum tubes. The tubes were German-made, the AF7 type, designed for radar receivers. He carefully removed one tube and inspected it. The construction was excellent, with a precise glass envelope and well-positioned electrodes, and the vacuum seemed perfect. He placed the tube in a tester, applied voltage, and measured its characteristics. It performed as expected: high gain, low noise. He tested 3 more tubes, all of which performed excellently. The German tubes were better than their British counterparts: lower noise, higher gain, and more stable. German tube manufacturing was superior. This made the radar more capable, more sensitive, and better able to detect distant targets. Jackson was impressed, but also concerned. If the German radar was this good, why weren't there more losses in Bomber Command? Why did any bombers survive? With such sophisticated equipment, the Luftwaffe should have been shooting down 15% of bombers, not 9%. There had to be some other factor, a limitation or weakness, that wasn't obvious from the individual components. He decided to test the whole system. He reassembled the receiver, connected it to the antenna array, and powered everything up. The radar initialized correctly, and the display illuminated, showing a clean sweep. Jackson places a metal reflector at a known distance, and the radar immediately detects it, providing a clear return signal with accurate range indication. He moves the reflector, and the radar tracks it smoothly. The system is performing perfectly. For 5 minutes, Jackson conducts tests, adjusting target positions and angles. The radar functions flawlessly. Then, something strange happens. The display flickers briefly, and the return signal weakens, then recovers. Jackson watches carefully and notices it again after a few minutes. The signal flickers and weakens, but it always recovers. This pattern repeats irregularly, sometimes every 2 minutes, sometimes every 5. Jackson stops the test to troubleshoot, checking connections and measuring voltages. Everything seems normal. He restarts the test, but within minutes, the flickering returns. He isolates components, bypassing stages to pinpoint the problem. After 2 hours, he narrows it down to the receiver amplifier stages, specifically the high-gain RF amplifier tubes, which had previously tested perfectly. He removes one tube, examines it, and finds nothing wrong. He places it back in the tube tester, powers it up, and the tube works perfectly again. No flickering, no signal loss, stable operation. However, under actual operating conditions in the radar receiver, the tubes intermittently fail, showing brief moments of reduced performance. Jackson realizes that the tube tester applies steady voltage with no vibration or mechanical stress, unlike the conditions in an aircraft. The tubes experience constant vibration, with engine vibration, airframe movement, and turbulence. Jackson decides to test the tubes under more realistic conditions. He mounts a tube in a holder, connects it to test equipment, places the entire setup on a vibration table, and starts the vibration. He observes the tube's performance on an oscilloscope. At low vibration frequencies, the tube performs normally. As he increases the vibration frequency, at around 85 Hz, the tube's output drops dramatically. The gain decreases by 60%, and the signal on the oscilloscope collapses. He stops the vibration, and the tube recovers immediately, with gain returning to normal. He repeats the test, and the same result occurs. The tube fails at 85 Hz, but works fine below and above that frequency. Jackson quickly understands the issue: mechanical resonance. The tube's internal structure vibrates at its resonant frequency, causing the electrodes to move and changing the tube's electrical characteristics, reducing its gain. When the vibration stops or shifts frequency, the tube recovers, but when it's at resonance, it becomes nearly useless. He tests the other tubes, and they all show the same problem. The resonant frequency is around 85 Hz, causing a significant gain reduction during resonance. This is a fundamental design flaw. The AF7 tubes are excellently made with perfect electrical performance under static conditions, but are mechanically vulnerable. The aircraft's engine vibration creates harmonics that match the 85 Hz frequency. Every time the vibration hits this frequency, the radar loses most of its sensitivity. The radar continues operating and the display continues showing, but the detection range drops from several kilometers to about 1 km. Targets that should be visible disappear, and the night fighter loses contact with the bomber. By the time the vibration changes and the tubes recover, the bomber has evaded. The night fighter crew believes the bomber performed evasive maneuvers or that there was jamming, but they don't realize their radar is being defeated by their own aircraft's vibration. Jackson writes a preliminary report dated July 19, 1943, documenting his findings. The report explains the resonance issue, the testing methodology, and the operational impact. The conclusions are significant. The German Liechtenstein BC radar is an excellent design but compromised by a critical flaw in the AF7 vacuum tubes. The tubes suffer severe performance degradation when subjected to vibration at their resonant frequency of approximately 85 Hz, which is within the range of normal aircraft vibration. This causes the radar detection range to decrease by 70–80% during resonance events, which typically last 10 to 30 seconds. The frequency of these events depends on flight conditions, but they likely occur multiple times during an intercept. This explains reports from bomber crews about German night fighters breaking off attacks without apparent reason. In reality, the night fighters weren't breaking off. They were losing radar contact due to tube resonance. The results were consistent. The resonance was repeatable. When asked whether it was a manufacturing defect or a design flaw, Jackson confirmed it was a design flaw. All AF7 tubes exhibited this characteristic, which was inherent to their mechanical structure. Could the Germans fix it? Jackson explained that they could, but it would require redesigning the tubes, retooling, and implementing new manufacturing processes, which could take months or even years. Did the Germans know about the problem? That was unclear. They might have attributed radar failures to other causes like equipment malfunction or operator error, and they might not realize the issue was vibration-induced. Jackson then proposed two ways to exploit this flaw. The first was tactical. Train bomber crews to perform specific evasive maneuvers when under attack, which would alter the aircraft's vibration frequencies. This could trigger tube resonance in pursuing night fighters, causing their radar to temporarily fail. The bomber could then evade during this failure. The second approach was strategic. This discovery altered how they assessed the night fighter threat. The German radar was not as effective as previously thought, not because of poor design, but due to this exploitable flaw. This could justify more aggressive bomber tactics. Harris quickly made decisions based on Jackson's report. First, he ordered Jackson's findings to be circulated to all bomber group commanders on a classified, secret, and limited basis. Bomber crews needed to be informed. Second, Harris authorized the development of recommended evasive maneuver procedures, working with test pilots to find maneuver profiles that maximized vibration at critical frequencies. Third, Harris instructed ongoing monitoring to detect any modifications by the Germans to their radar or the introduction of new tubes. The advantage would only last as long as the flaw remained. Within 2 weeks, new tactical guidance reached RAF bomber squadrons. The instructions were carefully worded to avoid revealing the source. Bomber crews were told to execute coordinated turns, altitude changes, and rapid maneuvers every 20 to 30 seconds, varying throttle settings. These actions would disrupt enemy tracking. The guidance never mentioned radar or tube resonance, just ordering crews to maneuver aggressively. The crews followed the orders without fully understanding why, but it helped them survive. And indeed, bomber loss rates began to decline. In August 1943, the loss rate dropped from 9% to 7%. By September, it was down to 6%. The decline was gradual but consistent. Harris attributed it to the new tactics, as well as other factors like improved electronic countermeasures, better bomber defensive armament, and a decline in Luftwaffe pilot quality. However, exploiting the tube resonance issue was significant. Every time a bomber maneuvered at the right moment, the pursuing night fighter's radar failed temporarily, allowing the bomber to escape. The night fighter crew had no idea why they lost contact. They assumed it was due to equipment malfunction, maintenance issues, or interference. They never realized their radar was being defeated by the predictable mechanical resonance of their own tubes. By late 1943, German records showed increasing complaints about radar reliability. Maintenance reports noted intermittent failures, and pilots reported targets disappearing without explanation. The Luftwaffe Technical Services launched an investigation, but found nothing wrong with the equipment. They tested radars on the ground, where they worked perfectly, and installed new tubes, but the problem persisted. The investigation focused on electronic interference, British jamming, and atmospheric conditions, but no one considered testing the tubes under vibration. The British kept their secret carefully, and Jackson's report remained classified. The information was not shared with allies or published in technical journals. Only a small group of people knew, as the advantage was too valuable to risk compromising. As long as the Germans did not realize their tubes were vulnerable to mechanical resonance, the flaw could be exploited. The secret held throughout 1943 and into 1944. British bomber crews continued using the evasive maneuvers, surviving at rates higher than the radar performance should have allowed. German night fighter crews kept experiencing mysterious radar failures and continued losing targets at critical moments. They blamed equipment problems and interference, never realizing their radar was being defeated by the resonance of their own equipment. In early 1945, Germany introduced a new radar system, the WW2 Liechtenstein SN2, with different tubes and a different frequency. Jackson obtained one in March 1945 and immediately tested it. The new tubes did not show the resonance problem, as they were constructed differently with a higher resonant frequency, above 200 Hz, outside the range of normal aircraft vibration. The vulnerability was gone. However, by March 1945, Germany had already lost the war. The new radar came too late to change the strategic situation or save the Luftwaffe. After the war, Jackson continued his work in radar and electronic warfare. He was awarded the Air Force Cross for his contributions, though the citation remained vague and did not specify what he had done. The tube resonance discovery remained classified until 1958, and when it was finally declassified, few knew about it. People eventually noticed Jackson's work. His findings were published in technical journals and archived in military libraries, primarily for specialists, and were largely ignored by general histories. Jackson retired from the RAF in 1947 and returned to Oxford to continue his research in spectroscopy. He published papers on atomic physics and became a Fellow of the Royal Society. However, his wartime contributions were never publicly acknowledged or celebrated. When colleagues asked about his work during the war, Jackson would simply say, "radar research," and if pressed further, he would deflect, citing the classified nature of much of his work. By the 1950s, most of his wartime research had been declassified, but Jackson preferred not to discuss it. He didn't want to remember the calculations or think about how many bombers survived because of his discovery. He didn't want to dwell on how many German night fighter pilots died frustrated, unable to understand why their radar failed. The technical work had been fascinating, but the consequences were grave. Both were true. In 1978, a graduate student named Peter Williams was researching electronic warfare history for his dissertation. He read Jackson's declassified reports, realized their significance, and contacted Jackson to request an interview. At 74 years old, Jackson was retired, spending his days reading and tending to his garden. He reluctantly agreed to the interview. Williams visited Jackson one September afternoon. They sat in Jackson's study, surrounded by books, old papers, and photographs from Oxford before the war. Williams asked Jackson about the Lichtenstein radar analysis. Jackson described the intact radar, the initial tests, the discovery of the tube resonance, and the realization that the flaw was exploitable. Williams asked the obvious question: "How many bomber crews survived because of your discovery?" Jackson paused, then answered, "I don't know. Hundreds, maybe thousands. The loss rate decreased. Part of that was my work. Part was other factors, impossible to isolate." Williams pressed further, asking if Jackson felt proud of his contribution. Jackson thought carefully before replying. "Proud? No. Satisfied? Perhaps. I found a weakness. Others exploited it. Lives were saved. That's sufficient. Pride seems inappropriate. I was doing physics, analyzing components. The strategic implications were someone else's responsibility. If you're fascinated by how technical details shaped massive battles, this channel is for you. We dive deep into the engineering secrets that history often overlooks. Subscribe and activate notifications as we release detailed analyses of World War II equipment. Equipment twice a week. Click subscribe now and don't miss the next video. Williams included Jackson's story in his dissertation, published in 1980. The dissertation didn't attract much attention. Academic work rarely does, but a few historians and researchers working on bomber command history read it. They incorporated the information into their work. The tube resonance discovery quietly entered the historical record, not prominently or dramatically, but as part of the larger story of the night bombing campaign. The story of British bombers over Germany, of German night fighters trying to stop them, of electronic warfare, and the small technical details that determined life or death. Jackson passed away in 1982 at the age of 78. His obituary in the Times mentioned his work at Oxford, his contributions to spectroscopy, and his fellowship with the Royal Society. It briefly mentioned his wartime service, stating, "During the war, Professor Jackson contributed to radar development." That was all. No mention of the Lichtenstein radar analysis, no mention of the tube resonance discovery, and no recognition of the hundreds of bomber crews that survived because Jackson understood physics. The information was available in archives, in declassified reports and dissertations, but it wasn't widely read or prominent. The story of the German night fighter radar and its fatal flaw remains obscure, yet the technical lessons remain important and relevant. Modern electronic systems are far more complex than the radar systems of the 1940s, but the principles haven't changed. Systems have failure modes. Components have vulnerabilities. Mechanical stress affects electronic performance. Vibration matters. Understanding these factors can reveal exploitable weaknesses. Military forces worldwide study the history of electronic warfare. They analyze Jackson's methods, how he systematically tested enemy systems, identified vulnerabilities, and exploited them. This approach won battles in 1943, and it wins battles today. The technology changes, but the process does not. Jackson's work exemplifies this. He didn't have sophisticated computer modeling or advanced simulation tools. He had captured equipment, basic test instruments, and methodical thinking. That was enough. Enough to find a flaw the German designers had missed. Enough to save bomber crews. Enough to change the balance in the night bombing campaign. Modern militaries apply these principles constantly. Captured enemy equipment is analyzed exhaustively. Every component is tested, every characteristic measured, searching for the vulnerabilities that can be exploited. The Afghan and Iraq wars and conflicts worldwide involve this very process. The same process applies today. Find enemy equipment, test it, understand it, and exploit it. While the technology has evolved, the methodology remains rooted in World War II. 2 practices. Jackson's legacy continues through engineers who never heard his name but follow his process. These engineers test enemy systems, subject components to stress, and identify vulnerabilities, unknowingly following Jackson's methodology. This is how knowledge transfers through generations, not through fame, but through practice, by solving similar problems using similar methods. The German perspective on the Liechtenstein radar emerged decades after the war. Former Luftwaffe night fighter pilots wrote memoirs describing their frustrations with radar failures, targets disappearing, and intercepts that failed inexplicably. For years, they attributed these issues to British electronic countermeasures, jamming, or interference. The truth about tube resonance was not widely known in Germany until British documents were declassified in the 1960s. German engineers who worked on the Liechtenstein radar reviewed Jackson's analysis. Some were surprised, others embarrassed. The flaw, in retrospect, was obvious. It should have been discovered during development and testing, but it wasn't. Why? Inadequate testing under realistic conditions. The AF-7 tubes had been tested on laboratory benches in static conditions, where they performed excellently. They were tested in aircraft on the ground with engines running, where they still performed adequately. However, they were never tested in actual flight under combat conditions, with heavy maneuvering, turbulence, and the full range of vibration frequencies that exist in aircraft. Had they been tested in these conditions, the resonance problem would have been discovered. The 85 Hz frequency would have been identified as critical, and the tubes would have been redesigned before deployment. But the radar was deployed based on ground testing and limited flight testing. The flaw only became apparent once the system was operational, by which time thousands of tubes had already been produced and hundreds of aircraft were equipped. Changing the tubes would have required massive logistical changes, new manufacturing, new testing, and months or years of development. Germany didn't have the time. So, the flawed tubes remained in service, causing German night fighters to fail in their mission, allowing bombers to escape when they should have been intercepted. This pattern repeats throughout military history. Equipment tested inadequately, deployed with hidden flaws, and failures blamed on other factors. The truth emerges slowly, if at all. The Liechtenstein tube resonance is just one example, though it is particularly well documented. Jackson's reports survived, were declassified, and provided clear evidence of what happened and why. If you're still watching, it means you care about understanding these stories properly. You don't just want to know that German radar had problems, but exactly what the problems were, why they occurred, and how those problems were discovered and exploited. This channel is for people like you, those who want in-depth technical details, engineering analysis, and the real stories behind these historical events. If you haven't subscribed yet, do so now. Every video reveals another technical secret, another engineering failure or success. Every video explains how materials and physics determined who won and who lost. Click subscribe, activate the bell, and don't miss the next video. Modern electronic warfare owes much to pioneers like Jackson. The methodologies he developed, systematic testing, thorough analysis, and understanding of failure modes, are the foundation of how militaries now approach electronic systems analysis. The principles Jackson applied in 1943 remain the same today. Capture enemy equipment, test it exhaustively, understand every component, and find its weaknesses. Today's electronic warfare analysts do essentially what Jackson did in 1943. The equipment has changed. Radars are digital now. Solid-state technology has replaced vacuum tubes. But the methodology remains the same. Test under stress, look for failures, understand failure modes, and exploit vulnerabilities. The defeat of Syrian air defense systems in 1982, Iraqi air defenses in 1991 and 2003, and Serbian air defenses in 1999 all involved the same approach Jackson pioneered. Captured systems were tested, weaknesses identified, and countermeasures developed. These results demonstrate the power of systematic technical analysis. Jackson never lived to see many of these applications. He passed away before most of them occurred. But his intellectual legacy continued through students he never taught, engineers who read his declassified reports, and military analysts who studied his methodology. The knowledge Jackson developed, propagated, evolved, and remained relevant even 8 decades later. The Liechtenstein BC radar itself is now in museums, carefully preserved behind glass. The Imperial War Museum in London has an example, and the National Air and Space Museum in Washington displays components. The placards describe the radar's capabilities, explain how it worked, and mention that it was used by German night fighters. However, they do not mention the tube resonance flaw. They do not mention Jackson's analysis. This information remains obscure and known only to specialists. The placards state that the radar was eventually countered by British electronic warfare measures, which is technically true. Jackson's discovery was a form of electronic warfare, but the placards do not explain the mechanical resonance, nor do they describe how vibration defeated the radar. That story is too technical, too detailed, and too specialized for general museum visitors. For general museum audiences, the real story remains untold. Visitors see the radar and recognize it as an impressive piece of German engineering, but they don't realize it was defeated by understanding physics, defeated by one physicist using test equipment and systematic methodology. The Junkers Ju-88 that carried the radar to England survived the war, was preserved, and is now at the RAF Museum in Hendon. Visitors can see the night fighter, can see where the radar was mounted, but the radar itself was removed for analysis and never reinstalled. The aircraft is impressive, but the real story isn't the aircraft. The real story is the radar, the tubes, the resonance, and how Jackson exploited that flaw. That story remains in archives, not museums. The Ju-88 in the museum prompts questions. Why did this plane land in England? The exhibit simply says, navigation error, with the crew disoriented and lost. This answer is partially true, but incomplete. The true story is one of operational security. The crew didn't know about the tube resonance problem, didn't know British intelligence desperately wanted their radar, and didn't realize that landing intact handed the British a treasure. They thought they made a mistake landing at the wrong airfield. They never knew their mistake would change the air war. The families of bomber crews saved by Jackson's discovery never knew either. They didn't learn that their loved ones survived because a physicist found resonance in vacuum tubes. When families received word that their loved one came home, it seemed like luck, skill, or divine intervention, not physics, not a design flaw in enemy equipment. The real reason remained classified and unknown to most families. Even today, some descendants of RAF bomber crews research their relatives' service, visit archives, and might come across mentions of new evasive maneuver tactics introduced in August 1943. But they won't find explanations. They won't discover the tube resonance story unless they specifically research electronic warfare. The information exists, but it's not emphasized or part of popular narratives. The Liechtenstein radar story is important for understanding the battle over Germany, how technical analysis shapes warfare, and for honoring Jackson's work in saving lives through understanding physics. But the story remains largely untold, known only to specialists and hidden from general audiences. This video aims to change that, bringing technical stories out of archives and into accessible formats for those who care about how engineering decisions determined battles, how physics affected survival, and how understanding resonance at 85 Hz meant the difference between life and death for a bomber crew over Hamburg. That's the story of Wing Commander Derek Jackson, the Liechtenstein BC radar, AF-7 vacuum tubes, and mechanical resonance. It's about how finding one technical flaw changed the night bombing campaign, how German night fighters lost targets they should have intercepted, and how bomber crews survived missions they shouldn't have. It's about how physics, engineering, and systematic analysis saved hundreds or thousands of lives. It's a story that deserves to be remembered. though it largely isn't, except in technical histories, declassified reports, and channels dedicated to revealing the engineering that shaped the war. This video is ending, but the story continues. The next video in this series reveals another critical German equipment failure that British engineers discovered and exploited. Another technical secret that changed battle outcomes. Another story of how small details determine big results. Subscribe now so you don't miss it. Click the red subscribe button below, activate notifications, and leave a comment telling us which German technology you want analyzed next. Panther tank armor, Tiger transmission, MiG-62 jet engines, tell us in the comments. We read every comment and build content based on what you want to learn. Subscribe now, and we'll see you in the next video, where British metallurgists reveal why Germany's most feared tank kept breaking down before reaching the battlefield. The metallurgy will shock you. The engineering failure was catastrophic. As always, the details matter. The story of Derek Jackson and the Liechtenstein radar ends here, but Jackson's methodology continues. In every military lab analyzing enemy equipment, in every engineer testing components under realistic stress, in every analyst finding exploitable flaws, the work continues. The technology changes, but the principles remain. Test systematically, understand thoroughly, exploit mercilessly. That's how technical intelligence wins wars. How it won the air war over Germany in 1943. How it wins wars today. Jackson understood this, applied it brilliantly, saved lives, and never sought recognition. He just did the work. And that was enough. That's the lesson. Not glory, not fame. Just competent, systematic analysis applied to save lives. That's what Jackson did. And that's what this channel celebrates. The engineers, the analysts, the scientists, the people who win wars through understanding how things work and finding ways to make enemy things stop working. Subscribe now for more stories, more engineering, more physics, more chemistry, and more technical depth than any other channel provides. WarTech Archives, where engineering meets history, where technical details matter, where we explore how things work and why it matters. Subscribe now. You belong here.